just let me tell you about this place here. This is what we call a mountain. It's called Scarfell. It's an absolutely idyllic place. When I say it's a mountain, it's 3,000 feet high. It's less than 1,000 meters in height. So you may laugh at that and say that's not a mountain, but to me that's a mountain. It's in a place called the Lake District in England, in the north of England, and it's a very, very favorite place. Right. Okay, I haven't received the sheet of answers for the problem that I set yesterday, so we'll do that tomorrow. And you'll be very pleased to know that there is no homework for tonight. So you don't need to slave until midnight tonight. But there will be some tomorrow. Okay, what we were talking about yesterday was transition state theory. And we were talking about potential energy surfaces, and we went through this. This is a potential energy surface for carbon dioxide. So CO2, linear triatomic molecule. There are three variables: the bond lengths and the angle of bending. And this is a diagram at a fixed angle. So the angle isn't changing in this case. And what we said was there's a potential well here. And at equilibrium, CO2 sits at the bottom of the well. And if you move in either direction here, along these dotted lines, then the energy increases in either direction. In other words, there's a restoring force taking CO2 back to its equilibrium position in a classical sense. And you can extend this bond distance and go out to O plus CO, and this bond distance and go out again to O plus CO. And if you go in this direction, then eventually you finish up with atoms. And this is what we call the symmetric stretch, where both R1 and R2 are increasing together. And this is the asymmetric stretch, where one is decreasing and the other is increasing. And the other vibrations are bending vibrations, and we can't show them on this diagram because it's at a fixed angle. Okay, then what we did was to go and look at a schematic figure for a reaction. And this is a reaction between A and BC. So these are the reactants, and this is the AB bond distance. And this is the equilibrium BC bond distance. And then as we come along here, what happens is the energy increases, reaches a maximum at this point if we're just moving along what's called the reaction coordinate. And then it decreases and we go out towards the products. And this is with the BC bond distance increasing and the AB bond distance staying very much the same. Someone commented at the end yesterday that it's a strange symmetric surface. Well, it is a symmetric surface. It actually refers to this well-known reaction H plus H2 goes to H2 plus H. You can actually measure that, the rate of that reaction using various devices, but I thought that just calling them A and BC would make things a little easier to understand. So it's symmetric because it's taken from this actual surface here. But this is the transition state. And if we move out in this direction here, which if you remember is the symmetric stretch for the molecule for the transition state ABC, then the energy increases in both directions. There's a restoring force. It's a genuine, proper vibration. But if you go in this direction along here, then this is at a maximum. So we've got two contrasting situations. We've got this as far as the asymmetric stretch is concerned, and this as far as the symmetric stretch is concerned. So this is a genuine vibration. This is not a vibration, it's more like a translation, but if you do a calculation, then what it does is it returns what's called an imaginary frequency. It gives you a frequency which is related to the curvature of this potential energy curve, but it's imaginary. It's an I in front of it. And that's the reaction coordinate. Okay, so let's see what the notes say. Reactants approach as RAB decreases, products separate as RBC increases, and the figures related to, again, to a fixed angle of approach. The symmetric stretch, where these both increases at a potential minimum, this is a true vibration. The asymmetric stretch is not. It's at a potential maximum, and this is the reaction coordinate. And we take, when we do, we haven't gone through quite where transition state theory comes from, but when you do, you take out this vibration, you take out this imaginary vibration, or effectively a translation, and it becomes this KT over H term here in the expression. And so there's the final expression for the rate constant in transition state theory. These, remember, are partition functions divided by volume, and alpha is an extra factor, and primarily it's used to describe quantum mechanical tunneling. Okay, what I'm going to do now is go very quickly and briefly through a discussion of the way in which potential energy surface calculations are carried out. If you look at a paper calculating a potential energy surface, then there's a lot of nomenclature there, a lot of letters floating around. And I don't want to go through this in any detail. I don't want you to feel that you've got to understand this totally. I'm just going to give you a brief rundown of some of the issues that are involved in doing these calculations. So when you're faced with these various notational effects, then you're not too worried about what they all mean. Okay, so we need to calculate the potential energy surface to determine the energy of the transition state, its geometry, and to determine the moments of inertia, because we need those for the rotational partition functions, and its vibrational frequencies. We also need these quantities for the reactants. For many kinetic problems, this reduces to determining these properties at the maximum in the transition state. So all we need to do is look at the reactants and the maximum in the potential energy surface along the reaction coordinate, that transition state. More information is needed if we're dealing with what's called variational transition state theory, which we'll talk about later on. So this requires us to solve the Schrödinger equation, and this is a difficult task, and we have to make approximations. And some approximations are better than others. Increasingly, the approximations are really very good ones, and very accurate calculations can result. Okay, so this is a diagram that comes from a paper written by Judith Zador, and it tells you what we're doing is we're moving into more accurate electronic structure calculations as we go down here. And let's see what's going on. A basis set is composed of atomic orbitals. So what we do is we've got a molecule, and it's made up of a set of atoms, and each of these atoms has got, when they're separated, they've got a set of atomic orbitals. So for example, we talked about the oxygen atom, and we said that it was 1s2, 2s2, 2p4. And that's an electronic configuration for an atom. So we're doing this now for a molecule, but we're using these atomic orbitals in order to describe the molecular orbitals. It's called a linear combination of atomic orbitals approach. And what's called the CBS limit, the complete basis set limit, is an extrapolated estimate of a result obtained using an infinitely large and complete basis set. Now, just let's see what we mean about this. If you were to describe an atom, the oxygen atom, then you wouldn't just use those orbitals. You need to use some of the higher energy orbitals because they have an impact on the atom as well. So you need to use many more orbitals than just that. And so this is what's going on down here. So this is using an increasingly large number of atomic orbitals to describe the molecule. And the complete basis set limit is where we're using, by extrapolation, all of the conceivable orbitals that we could use. Now, in addition to that, these electrons in these different orbitals interact with one another. An orbital is a one-electron description. But the electrons in the different orbitals interact with one another, and they interact with them through something that's called electron correlation. The correlation energy is a measure of just how much the movement of one electron is influenced by another. And so what we're doing as we go along here is we're allowing for this electron correlation with different methods. And those of you who have read papers, and I'm sure many of you have, then you'll recognize some of these sets of initials as we go along here. The Hartree-Fock method, which is the least accurate and the oldest method, has minimal electron correlation. Full configuration action, or full CI, can be obtained using a variational approach. And so what you want to do is to move along in both these directions so you get a more and more accurate representation of the energy of the system for a particular geometry of the molecule. And then you change the geometry and you do the energy calculation again. It doesn't stop there, because this is what's called, this would be a single reference arrangement of the electrons in the orbitals, but there might be another representation involving a different set of orbitals that has a similar energy. And these two interact with one another. And so what we have to do is something that's called use multi-reference techniques, where these interactions are important. And they're important in many of the radical reactions that we're dealing with, especially things like methyl plus methyl and say ethyl plus O2. These require significant multi-reference aspects in the calculations that you're dealing with. So multiple wave function descriptions are needed to describe just a single transition state then. And examples of these are CAS-SCF and CAS-PT2, and these will keep cropping up as we go along today. There's also something called density functional theory, which is completely different from ab initio theory, which we've just talked about now. And instead of using orbitals, what they use are functionals, which are empirical quantities that have been optimized to describe molecular systems as accurately as possible. And one of these functionals is called B3-LIP, and these are more recent ones, MO6-2X and MO8. And these DFT calculations can be done really very quickly. And you use DFT calculations to explore potential energy surface and decide where the maximum in it is. So where the transition state is, where the maximum along the reaction coordinate is. And having found that, you then go to a higher level of theory. You then go to ab initio calculations and use some of those methods I've described before to optimize that energy. And sometimes you also need to change slightly the position of the transition state. So it's then used to refine, in particular, the energies of the turning points on the surface. Approach to calculating rate coefficients using TSD. The approach is most simple for a constrained transition state, and that's one where there's a significant maximum, and we can say with some confidence that that's where the transition state is. And so you then calculate the potential energy surface using electronic structure methods. You determine the energy, the vibrational frequencies, and we generally or in the past certainly, have used something called the rigid rotor harmonic oscillator approximation. And this means that we're treating all of the vibrations as harmonic oscillators. We said yesterday that they are actually anharmonic, but most calculations use a harmonic oscillator approximation. And we assume that the molecules, as they rotate, are rigid. And so these are approximations, and it's called RRHO. Problems arise with hindered rotors. I'll say a little bit more about this later on. And quantum mechanical tunneling through the energy barrier can be important for H transfer reactions, but not for other sorts of reactions. So we talked about this diagram here, and here's our expression for the transition state theory. But remember that this diagram is for a triatomic system, and it's even constrained on that because we're not allowing the angle to change. And for bigger molecular systems, then the potential energy surface is obviously going to be very, very much more complex and much more difficult to represent. Okay, a reminder of the partition functions that we've talked about over the last couple of days. Translation, rotation for a diatomic, rotation for a polyatomic, for a nonlinear polyatomic, vibration for one vibration, say a diatomic molecule, and then for multiple vibrations, and the electronic partition function. Remember, sigma is the symmetry number, and G is the degeneracy of these levels when we're talking about electronic motion. So just let's have a look at just how this would pan out for a simple example. So we're going to look at O plus RH going to HO, HR, eventually forming water, and R, and there's the transition state. So we'll write the transition state as X, just to make life a little bit easier. And there's the rate constant expression. And what do the translational partition functions look like? Well, there's Q, which is little q over V, 2 pi mkt to the 3 over 2 over h squared. Let's now write it out for everything, for X, the transition state, for OH, and for RH. And we get this ratio of masses and a temperature dependence, which is T to the minus 3 over 2. Okay? I'll come back to that later on. So for the translational energy contribution gives rise to this mass term and also this very important numerical term here, but a T to the minus 3 over 2 temperature dependence. So this is the translational contribution to the partition function. Rotational contribution, that for OH is a heteronuclear diatomic molecule. QOH is KT over sigma HBc. Sigma is unity because it's heteronuclear. And so we finish up with an expression that looks like that. If we go to the to RH and X, these are nonlinear polyatomics. And there's the expression for their partition functions, where these are the rotational constants which are proportional to the appropriate moments of inertia, the x, y, and z moments of inertia. And so if we take the ratio of those, qx over qrh, we're going to finish up with the ratio of the symmetry numbers. So the symmetry numbers are really important in describing these transition states and calculating the values, and then just the ratio of the moments of inertia. So these depend upon the ratio of the geometries of the molecules, the sizes of the bond, the sizes of the molecule, and the angles that are involved. So we need geometries to obtain moments of inertia, and we can obtain these from spectroscopy for stable molecules, but for electronic structure calculations, you can use electronic structure calculations for X. When I was a graduate student, people couldn't do electronic structure calculations. It was rather a long time ago. And we used to guess them. So we just guess the geometries. And so it was a very, very inaccurate activity. And experiments were supreme. They ruled the roost, and you might use transition state theory to try and understand a little bit about what was going on. But now things have changed dramatically, and you can get these quantities really very, very accurately from electronic structure calculations. Vibrational and electronic contributions, as far as OH is concerned, we've just got a single vibrational mode. So this is the vibrational frequency in wave numbers for OH. For RH and X, it's going to be something like this, where N, the number of vibrational modes, is 3n minus 6 for RH, and 3n plus 2, because we've got N is the number of molecules in RH, and number of atoms in RH, but we've got 2 more coming from OH, and then we reduce that by 7, 6 because it's a nonlinear molecule, and another 1 because we've taken a vibration out of the expressions because that's going over the along the reaction coordinate and over the transition state. The electronic partition function for OH, we discussed this yesterday. That's going to be G1 plus G2 exponential of minus delta E over KT. The G's are 2. So that's an important consideration. Electronic partition function for RH is unity. It's a stable molecule with no unpaired electrons. The electronic partition function for X is going to be 2 because there's a single unpaired electron that's come in with the OH. Sorry, just let's go back to here. Here what we've got is the only temperature there's no temperature dependence in these. There's a temperature dependence coming from the OH. It's going to be a T, coming from the OH, it's going to be a first power of T, but it's going to go in the bottom line, so it's going to be another T, it's going to be a T to the minus 1. So we've had a T to the minus 3 over 2, and now a T to the minus 1. Okay, so this needs a bit of explanation. This is just trying to explain what the effect of the frequency of the vibrations is on the frequency of a vibration is on the partition function. So we're going from temperatures of 200 up to 3000, and this here is the partition function for a vibration with a frequency of 50 wave numbers. And you can see that it starts off as a value of 3. The minimum value of a partition function can have is 1. So it starts off at 3.3 and goes up to 42. So quite big and a strong temperature dependence. And we go gradually across until at the end we've got 3000 wave numbers here. And the partition function there at 200K is 1.00. That's because all the molecules are sitting down in the lowest energy level. And then it increases, but it increases very slowly. And so you can see that the temperature dependence of the expression that we're calculating is going to depend very sensitively on the frequencies of the various vibrations we're dealing with. Another consideration is we need to worry about internal rotors. So this is the case of ethane. So we've got 2 methyl groups here, and they can vibrate against one another. And the energy is going to change as that angle changes, because if we consider 2 of them, when they're what's called eclipsed like that, then the energy will be high, and when they're staggered, they interact less, and so the energy will be lower. And so the potential energy is going to look something like this. Because there are 3 atoms, you can go around 3 times in 360 degrees. And these are the staggered configurations, and these are the eclipsed ones. Sorry, these are the eclipsed ones, and these are the staggered. So the staggered are lower in energy, and the energy barrier is of the order of 12 kilojoules per mole. Now, if we go to very, very low temperatures, then this system will behave like a vibration. So the 2 methyls will just be moving like that. But as we go up in temperature, then they'll begin eventually to freely rotate. But there's a hindered rotor situation as we move up there. And you can treat these, you can get essentially partition functions for these, but it's a little bit more complicated. But it's important that you understand that this is an issue. Now, okay, so this is an example, OH plus dimethyl ether. OH is abstracting a hydrogen atom. And these are data which are taken from this paper here. So I didn't put the reference in, so that's why there's a little star here. And so these are the data for OH, which are taken from spectroscopy. These are for DME, which ideally, again, are taken from spectroscopy, but these are actually calculated values. And then these are calculated values for the transition state. And there's the imaginary frequency, which refers to this non-vibration there. And these are experimental results taken from that paper and calculations using transition state theory with some tuning of the parameters. And so these are the data for OH plus dimethyl ether. And these down here are the data for OH plus deuterated dimethyl ether. The rate constant is reduced because of the deuteration. And this is the potential energy surface, which is a little bit more complicated than we said earlier on. And we'll come back to this later on and see some of the consequences of the complexity of that surface. And there are 3 transition states. That's not actually the case. There's really only, those transition states, those 3 transition states are linked because the OH is moving around the DME, giving different structures and different transition states, but they can communicate with one another by some sort of internal rotational process. So, and you've got to deal with that, and that's a complication, but it's possible to deal with it. And so essentially, there's this well here, there's a transition state here, and then you can do the calculations. And the calculations agree really very well with the experimental data that are available. Remember, we have tuned it, though. And notice that the rate constant curves quite considerably. This is an Arrhenius plot, quite a considerable amount of curvature. And part of that is due to tunneling through this barrier here. And that's a comment about how the calculations of tunneling have been done here, a detail. Now, I think one of the important things, and this cropped up in a discussion after the lectures yesterday, is to try to understand where temperature dependencies are coming from. There's the expression, there's a transition state theory expression. This is the difference in energy between the reactants and the transition state. So if there are only this barrier, then that delta E naught there would be minus 0.6. So this is e to the minus the difference in 0-point energies over kT. And then we have a positive temperature dependence from there. If If you remember, we had a t to the minus 3 over 2 from translation. We had a t to the minus 1 from rotation. And we've got a fairly complicated issue as far as vibrations are concerned, but it's going to give rise to some form of temperature dependence, but it's difficult to predict. You've got to go into the calculations in some detail. Now, those data there, you wouldn't publish all the, well, you publish all the details of this, but you would represent the rate constant in the usual sort of way. So in the paper, you would represent the rate constant as being equal to a t to the n, the exponential of minus EA over RT. And those parameters there are obtained by fitting, either to the theory or to the experiment. What you probably do here is fit to the theory because the theory has been fitted to the experiment. And you'd fit 3 parameters, A, N, and EA, and in themselves, they don't have, they are just fitting parameters. They don't have in themselves a fundamental meaning other than just they're representing the way in which the rate constant varies with temperature over a certain range. And in addition, especially for, I mean, if you look at this rate constant, it's varying by a little over a factor of 10 over a very, very wide range of temperatures, not by a huge amount. And there's quite a lot of correlation between these parameters here. If you fitted it in a slightly different way, you might get slightly different parameters. And so that's important to remember. The relationship between these parameters and the transition state parameters can be determined, but these are really just fitting parameters, not fundamental in their own right. Okay. Any questions? We've had half an hour. Oh, right.
So going back to internal rotors, so does the inclusion of internal rotors in your partition function cause the partition function to go up or down?
It depends upon the conditions. It's an interesting and really rather complex process. Usually it causes them to go up. But if you think... Oh, sorry, yeah. The question was, if you've got internal rotors in your transition state or in the reactants, if you incorporate those, does it cause the rate constant to go up or down? And my mealy-mouthed answer was that it's difficult to predict, and it depends. Usually it's going to, the key thing is the number of, the densities of states. We'll talk a little bit more about densities of states later on. And the densities of states usually increase when you go over to an internal rotor. But it can be somewhat complicated. But usually it causes it to go up.
Do these transition states have an actual structure to them? And if they do, can you predict or know what they are?
They do have a structure. And to predict it exactly without doing the calculation would be very difficult. But you can rationalize it. So you could rationalize these and look at you can look at the structure, the interaction between the OH and the DME, and there is a certain amount of interaction between them that you can understand through hydrogen bonding in particular, and so those differences in energy of those three interconnected transition states you can rationalize through the effects of hydrogen bonding. Okay, are you rested? Did you watch the Germany match with Heinz this morning? Did he show it during his lecture? He didn't. Sorry?
Just during the break.
During the break. So he did have it on during the break. Yeah, he's not very happy. So tunneling in chemical reactions. Reminder of a square barrier. We said that if you've got a square barrier and you're tunneling through it, then you can describe the wave function in terms of A e to the minus kappa x, where this is kappa, which is the potential energy minus the total energy, minus the kinetic energy. And note the dependence on mass. And so for our purposes, tunneling is only really significant for hydrogen atoms. The simplest calculations basically just use the shape of the barrier. So you get the imaginary frequency, and that tells you about the curvature at the top of the barrier, and then you use a parabola or a slightly modified parabola to describe the potential energy and look at tunneling through it. And that's a simple but not particularly accurate way of doing it. And the Eckart model is slightly more accurate. What is actually happening in this is that as we're proceeding along here, the hydrogen atom transfer occurs, and we go from a point here to an equivalent point over there. And that's the barrier you're going through. And you will come across discussions of this this will be mentioned in one or two of the examples I give later on. So tunneling is a little bit more complicated than just going through a barrier like that. Now, what we've just talked about is called canonical transition state theory, where we're referring to a particular temperature and to an ensemble of molecules distributed at various energies. It's also very useful to use what's called microcanonical rate theory, where what we're doing is we're looking at a particular energy. And this is the equivalent expression to transition state theory for a specific energy. And there's Planck's constant, and then this is the sum of states of the transition state. So what we're doing there is if this is the transition state, and we've got an energy up here, what we're doing is we're adding up all of the states that can be described between the top of the transition state and that energy E. And it's divided by the density of states, and the density of states is if you take a small energy gap of, say, one wave number in thickness, then the density of states is the number of states that occur in that gap. And I'll show you an example in a minute, which I hope will help make things clear. So WE is the sum of states of the transition state, so it's going to depend upon all the various states that can be generated, and you'll do that using the data that have come from your potential energy surface calculation. And NOV is the density of states at energy E. And we'll use this approach when dealing with master equation calculations later on. And integrating this expression over a Boltzmann distribution gives you the standard canonical transition state theory result. Okay, in order to understand what sums and densities of states are, let's look at methane. Methane has got 4 vibrational modes, frequencies 1306, 1534, 29117, and 3020 wave numbers. And this is what's called triply degenerate. There are 3 vibrations in there. This is doubly degenerate, that's singly degenerate, and this is triply degenerate. Now, just let's look at all the various states that we can assemble. So the first state we're going to assemble, so we've got the ground state there. And it's got a degeneracy of 1, and so the number of states is 1, and the sum of states is 1. We then move up, and the first vibrational level in the 1306 mode is going to give us another level, but it's going to be triply degenerate. So there are actually 3 states there. And so the total sum of states now is 4. 1 plus 3 is 4. The next one is going to be this one here, 1 quantum of vibration in there. It's doubly degenerate, so there will be 2. So we've now got a degeneracy of 2 at that state and a WE of 6. 1, 4 plus 2 is 6. And so on. So here we've got 1 vibration in mode 1, 1 in mode 2. So that's going to give us a total degeneracy of 3 from here times 2 from here. So there are 6 states at that energy. And by this stage, we've got up to a sum of states of 18. And so we carry on up. Here's 3 quanta in mode 1. And we won't go through exactly how you calculate the degeneracy, but it's a degeneracy of 10. It's the number of ways you can arrange them in these 3 different modes. So the degeneracy there is 10, and the sum of states by this stage has got up to 35. Okay, so that's what we mean by the sum of states. We're summing up all the states up to a certain energy. And then this is the density of states. This is the number of states per wave number. And so at this energy, we've got an average of 4. We've got 3 states around about here, and we can divide that by the energy ranges that are involved and get a density of states. And the density of states is really very small. So the density of states is telling us the average number of states in this case over a 1 wave number range. As we go up and up in energy, then we get more and more and more vibrations. You can see that these numbers of vibrational states is increasing as we go down here. And so as we get up towards sort of chemical energies, if you like, dissociation energies, then we have lots and lots of states, high densities of states, and high sums of states. And we can use those to calculate the rate constant. The accuracy of transition state theory calculations, typically it's of the order of barrier height of 4 kilojoules per mole. And so what I've done here is take the exponential of E over RT, basically putting this into an activation energy term. And if we look at E to the 4 over RT as a function of temperature, you can see that temperatures above about 500 K, it's not having a desperately strong effect. But lower down, it is because of the 1 over T term. So at low energies in atmospheric calculations, then these terms are really this uncertainty is really quite important. But it's getting less and less important as you get up to combustion temperatures. There can be deficiencies in the transition state theory model. I showed you that OH plus DME, and it's really quite difficult to deal with those 3 related apparent transition states, and that can lead to errors. The rigid rotor harmonic oscillator model may not be appropriate, and the tunneling model may not be as accurate as it should be. There are ways of making things better, and often, I mean, the sort of calculations that we do, because we're experimentalists, what we're doing is we're usually tuning the barrier height or some other aspect of the calculation to the measurements that we've made. But if you look at this paper in the Proceedings of the Combustion Institute, 2017 by Stephen Klippenstein, then you'll see a discussion of the accuracy of purely ab initio, but very high-level calculations. So just have a look at the effects of incorporating high-level methods. So if you want to look at high-level methods, then I'm going to give you 3 examples. So this is by John Barker, and is on OH plus H2, using high-level ab initio calculations, so the barrier height is obtained quite accurately, incorporating anharmonicity, and incorporating the coupling between the different modes and multidimensional tunneling. I said that you can you're going through the barrier in a slightly different way from that which you might expect. And you can do that in different ways, and that's multidimensional tunneling. And so here's the experimental data, and here's his calculation in red, which is his best calculation. And you can see that it's really very, very accurate. And then this is a series of calculations on OH plus OH going to O plus H2O by Stephen Klippenstein and taken from that paper that I referred to in the last slide. So this is an earlier calculation with a barrier height that's in error. This is with the barrier constrained to experimental data. So this is taking this calculation, constraining the barrier to experimental data, and getting a much better fit. The black is an absolutely ab initio high-level calculation where no assumptions, where no tuning to the experimental data has been used. And then the red one, which is the best fit of all, is where the high-level, these high-level transition state theory calculations have been constrained to experimental data, giving a barrier of 1 kcal per mole. This is a calculation by John Stanton using a method called heat, which he is the leading exponent. This is high accuracy extrapolated thermochemistry. And this is accurate to about 1 kilojoule per mole. And it includes a new treatment of tunneling. And it's a very good paper to read to understand how these high-level calculations are done. And the red one is the best calculation, and you can see that it reproduces the experimental data really very, very well without any tuning. And this shows the tunneling correction. And it's on a log scale. You can see that at 200K, the tunneling correction is about a factor of 10. So tunneling is occurring 10 times more quickly than going over the barrier. So it's really important. And as you go further down in temperature, then it becomes more and more significant. And of course, the reason is that at low temperatures, the term, e to the minus EA over RT, at low temperatures, this is a very, very small quantity. And so very, very few molecules have enough energy to go over the top. And if they can go through the barrier, then it's going to be much better. Okay, let's now have a look at radical-radical reactions. So those were all reactions occurring over a barrier. Radical-radical reactions, many of them do not have barriers. And so we have to worry about new things in order to determine just where the transition state is. And the calculations are done what's called variationally. So some reactions have only a small or no energy barrier. And in these circumstances, the exact location of the transition state is problematic. In canonical variational transition state theory, what you do is you maximize the Gibbs energy to find the transition state. So the transition state is going to be the bottleneck for the reaction. And the bottleneck is going to occur where we have the maximum Gibbs energy. And what that means, Gibbs energy is a combination of the enthalpy. So it's, to maximize G involves a combination of maximizing the energy term and minimizing the entropy term. So the transition state could be where it is because of either energetic or entropic effects. We'll see that in a minute. So the next slide examines microcanonical transition state theory and its variational form, which focuses on specific energy rather than temperature, as in the canonical approach. So this is CH3 plus H. And what's happening is that this reaction is occurring on a potential energy surface that looks something like that. So this is the CH3H bond distance, and they're coming in like this. And there's no barrier. That should be flat. There's no barrier, and the energy decreases. So what determines where the transition state is going to be? And what value does it have? Well, whoops. Initially, what happens at low energies, so this is an energy of 0.1, whatever units they are, the transition state occurs at the minimum of W, the minimum in the sum of states. And it occurs here at quite large distances. And then, as we move up in energy, the minimum goes down in energy, goes down in value, sorry, and occurs at much smaller distances. So this is actually the density of states as a function of distance. So this is the density of states as we come in divided by the density of states when they're widely separated. And so that minimum is the minimum in the density of states. Now, let's try and understand why that is. So what's going on? As the two species come in, then the energy decreases. But what's happening to the entropy, if you like, as these two species come in? This is CH3. Yeah, so we're going to look at CH3 plus H. Yeah. We're going to look at CH3 plus H. And here are the vibrational frequencies for CH3. We've got CH3 is a planar molecule. And it's got 3 CH stretches, pretty obviously, and those are the high-frequency ones. This is doubly degenerate, and that's singly degenerate, so the 3 vibrations. This one is what's called a deformation mode, where these angles here are changing. So we've got effectively 2 independent angles there, and they're changing as the molecule vibrates, bearing in mind that it's planar. And then finally, we've got what's called the umbrella mode, which is where these hydrogen atoms move out of the plane. So basically, the CH3 is, I can't really do it, but it's sort of doing that. So these H's are coming out of the board together, or they're going into the board together. And that's a low-frequency vibration, a frequency of 606 wave numbers. And this is methane. Methane, we've got 4 CH stretches, 1 here. This is triply degenerate, 3 there. And then these are deformation modes of various sorts. 2 of them there and 3 of them there. Okay, now what we're going to do is we're going to have a look at what happens as H comes in to CH3. And so that's reminding you of how many vibrations and rotations there are in a molecule, and we've done that many times, so I won't go through it again. And this is what happens. So this is CH3 and H going to the transition state. So we've got 3 translations in CH3, 3 in H, and 3 in CH4, 3 rotations in CH3, 3 in CH4, 6 vibrations in CH3, and 8 plus the reaction coordinate in CH4. So 3 of these translations will go over to 3 of translations over here. So that's pretty obvious. We'll see what happens to the others in a minute. 1 rotation here will go to 1 rotation there. So if we imagine the hydrogen coming in here, and this CH3 rotating like that, then that goes over to the rotation of the CH4 molecule. The next one are these 2 translations. So 2 of these translations here go over to rotations. And what's happening there is we've got the CH3 here, the hydrogen coming in here, and they won't necessarily hit head on. It might miss by a little bit, and that goes over to rotation. So that translation is going over to rotation in the transition state. And that will happen in this plane and also in the plane perpendicular to it. So that's now got rid of all the translations. 3 of them have gone over to translations there. No, I haven't quite got rid of one of them. 2 have gone over to rotations, and one of them, the H coming into the CH3 directly, goes over to the reaction coordinate. And then 2 of the rotations in the CH3 go over to deformations in the CH4. So you can imagine, here's the CH3, here's the H. The CH3 is rotating quite happily until the H gets closer, and then its rotation is restricted, and it goes over to some sort of deformation mode. And that can happen with 2 of these rotations going over to those. Now, the other deformation modes come from the umbrella motion. So that umbrella motion is this thing coming out, in and out of the board, and as that comes in, it's going to get towards the H, and it's going to become more and more restricted, and it will go over to a deformation. Remember, it's a very low frequency, 606 wave numbers in CH3. And the same with some of these deformation modes here. And then finally, the CH stretches go over to the CH stretches. One of the CH stretches has been lost in this reaction coordinate. Now, what does all that mean? Well, it means that, for example, here we've got translations which have got very, very high densities of states going over to rotations which have got much lower densities of states. We've got rotations going over to vibrations. And we've got low-frequency vibrations going over to vibrations. So as the molecule comes in, what is happening is that the densities of states are going to decrease. The spacings of the energy levels, the vibrational energy levels, are getting bigger. And so at a given energy, there are fewer ways in which we can distribute the molecules throughout those vibrational energy levels, so the densities of states goes down. And so that's, if you like, is the entropic effect. High entropy corresponds to high numbers, high densities of states. But as we come in, we're going to be decreasing the densities of states. So we're decreasing the energy, but we're decreasing the densities of states as well. And so that's what was going on here, where as we come in, the densities of states are decreasing, and there's the minimum, which is obtained by this interaction between the decreasing energy of the system and the changes in these vibrational frequencies. The same thing applies to, say, methyl plus methyl. So here's the methyl radical coming in to form C2H6. And these frequencies here are going to be transformed into these frequencies here. And you can do exactly the same sort of analysis of correlation as we did in the last one. Okay, just let me... No, let's let you off 2 minutes early, provided you agree to come back 2 minutes early as well. Okay, so I'll see you just before 1:15.